Let's say we have an 8-foot by 12-foot piece of cardboard. And we're going to make it into a box by cutting out squares from each corner, like so. Once we've done that, we're going to fold up each of these 4 flaps, and we're going to tape them together, and we'll have a box. There's no top to the box, and it might not be the sturdiest thing in the world, but it'll work for now. The question is, what's the biggest volume that we can obtain using this method? First, let's take a moment and think about why this is an interesting question. It's because there are trade-offs involved. If we cut very tiny squares out of the corners of the cardboard, then our box is going to be really wide, but incredibly short, and that's not a very large volume. But if we cut out really large squares out of the corners, then the box becomes really skinny, and that's no good either. The sweet spot has to be somewhere in the middle. Okay, this is an optimization problem because we're trying to maximize the volume, and the volume V is just given by length times width times height. It's a box. You might look at that and say, whoa, that's 3 variables there, length, width, height. How am I going to keep track of all of them? But the good news is that these aren't independent of one another. Everything here is determined just by a single quantity. It's determined by how big we cut these squares out of the corners. Once you know that, you know everything. So if we just call the side of this square x, then everything can be written as a function of that single variable x. And that's good because multivariable calculus is a whole other course. What we want you to do now is actually find what v is in terms of x exactly, and then determine what interval we're trying to optimize over, and then do it. We'll talk afterwards.